intermediate FTC coding workshop by myself, Jensen, and Sean from FTC Team 10635, Unknown Element.
Today we'll be covering three major topics: version control with GitHub, robot vision, and autonomous navigation, followed by a brief Q&A session. The first topic we're going to be covering is version control in GitHub. So let's start with, what is version control? Version control is a way to manage and save the changes to your project over time. The tool we'll be using for that is Git. Git is the industry standard version control system that we're going to be using, and it is also used by the FTC SDK. And then we're going to be using GitHub, which is a website that stores Git repositories safe away from your device. So there are three major reasons we should use version control. The first is protection. It provides a strong offline remote server that you can save your code base to. This has the advantage that if you lose your laptop, it breaks, or you delete your code, you always have a safe spot you can download your code from. The second reason is collaboration. It's a central working place for code. It allows you to push and pull work on files safely with your teammates. The third reason is experimentation. It adds retraceable steps in your code from known safe locations, so you can try different things and always revert back if something fails. We'll be covering three major Git topics, Git concepts. The first being a commit, the next being push and pull, and the final being a branch. So what is a commit? A commit is a saved snapshot of the changes of your code. It always starts with an empty working index that you can add changed files to. You can do this by staging modified files to the index. And then once you're ready to seal that and always add that as a safe point to come back to, you can commit it. So it's always something that is saved for your history. Next we have push and pull. Push is how you send all those local commits you just made to GitHub. And then pull is how you and your teammates can download those changes to each of your local devices. A branch. A branch is key to experimentation. It allows you to make changes to your code base without interfering with the main line. So you can always have a safe working program while working off to the side on both major and minor changes without affecting your safe spot. We're now going to be looking at a couple of Git commands in the command line. Your OnBot Java, Android Studio, and Visual Studio IDEs all have built-in ways to manage Git, but it's just a bit easier to visualize in the command line. We're going to start with this git status command. It's going to print out some basic information on your repository. The first piece of information we have is what our current branch is. We are currently on the branch master. This is generally considered your main line, or where you want to put the stable code. If we run our git branch command, it can list all of our available branches we could be editing code on right now. We next have the number of commits ahead of origin/master. This is our remote GitHub repository. So we have one local commit saved to our machine that isn't on GitHub. Next, we have our list of modified files that have not been added to the working index. These are files that have been changed, but you cannot commit right now. This is because our commit is empty. Our working index is empty. So if we were to try and commit right now, it would throw an error because there is no files. So let's say we are happy with what cycle warehouse code and our intake cube code does. We can add those to the index, and then we can commit that. Or let's say we completely mess up our cycle warehouse code. We can run git restore, and it'll revert that file back to its last known saved commit. So you always can work, and if it fails, you can always revert. The next couple of commands to suggest is git add and git commit-a. So we're going to look at this bottom command first. It's two commands, git add-u. That adds all modified files to the working index. And then you can run git commit, and that'll commit it, or add it, or seal it and save it. You can also do this in a single command with git commit-a, which does the same thing as those two commands below. And if you attach a -m argument followed by a string of text, it attaches a message to that commit. So if you go back through the commit history, you can see why you committed those files. So let's say you want to go back to your December meet and look at what you did there. You can look through your commit history and look for the one titled December meet final. Running this command, it's going to print out some basic information on our repository, like the number of files we changed and the number of lines we changed. If we run the git status command again, you can now see we have 2 commits on our local machine. And it also tells us our working tree is clean. That means there are no modified files in our project. It then offers us one final command, git push. This is how you're going to send that code to GitHub. It's going to take those 2 local commits and push it up to GitHub, so all other people within your team and access to your repository can now pull down those changes, and they can now work with them. It's going to print out some mostly useless information that just tells you it successfully sent it, so you can just ignore that. So setting up GitHub for your team. Your team coach or your head programmer is going to want to create a GitHub account, go to their settings, and then create an organization for your team. This is how you're going to add your other programmers and team members to the organization. From that organization's account that is newly created, you want to go to the first SDK, and you want to fork it. This is going to make a clean copy of their code that you can modify safely without modifying the rest of the SDK. And then each of your team's programmers are going to create a GitHub account and join your team's organization. They're next going to need to generate an SSH key. This is a secure communication between your laptop and GitHub. It's semi-complicated to set up. It just takes a bit, so we're not going to be going through it here today. You can look it up online. GitHub provides a nice step-by-step instructions for you to follow. And then for each of your team members, once they've been added to the organization and created an SSH key, you want to clone your team's repository down to your machine. You can do this in Android Studio or on Java, and it'll handle cloning it for you. So our next topic we're going to be looking at is robot vision, and we're going to be looking at a basic implementation of an OpenCV pipeline. In this case, we're going to be using the Freight Frenzy team shipping element problem from last year. On the left, you can see our final output, and on the right, we have a basic breakdown of our vision pipeline. The first thing we're going to do is convert the image from RGB to HSV. Then we want to create a mask of all color within a certain threshold, and then third, we're going to check 3 subzones we define. So what is OpenCV? OpenCV is an industry standard computer vision library. It allows you to take in frames from a camera, modify and process those frames so you can figure out an output from it. We're also going to be using OpenCV, which is an FTC specific library that makes working with OpenCV on the control hub slightly easier. So we're going to look at this class in an extends OpenCV pipeline. This is provided by Easy OpenCV. The next thing we're going to do is define 2 values, the upper and lower color range. These are scalar values. A scalar is a sample type that holds 3 values. In this case, we're going to be using a scalar for HSV. What is HSV? It is a color format that relies on 3 channels: hue, saturation, and brightness. It's a V, but it stands for brightness. The HSV is unique from RGB because it tries to split the brightness channel and the hue into 2 separate channels, versus RGB, which tries to simulate what the human eye would see. This has advantages in computer vision because it's not as heavily affected by different lighting conditions, which is very good for your robot competition where you might be under stage lighting or in a dark room. Next, we're going to want to define 3 areas we want to check. These are 3 rectangles within the frame of the camera. In this case, we were running a camera at 480p, so we were checking 4 specific areas within the 480p image. We're next going to look at this process frame method. It runs for every frame that comes in from the camera. The first thing we want to do is convert the image to HSV for the advantages we just discussed, and then we're going to create a mask from those upper and lower ranges of color we defined previously. So what is this going to do is any color within this range is going to be made white, and any color that is not in this range is going to be made black. That's how we got that black and white image we saw in the beginning. We're then going to return the input. We always need to be returning the frame we're modifying so that it can continue down the pipeline and the next frame can be passed in. But before that, we're going to run the process barcodes command. This is a simple method we wrote that is going to process which of the 3 barcodes contain our team shipping element. So the first thing we're going to do is we're going to make a submat. A submat is an image within an image. So it's going to take that small zone we defined and turn that into its own image for us to process. And with that, we're going to take the average of all 3 of those channels. So we're going to average the hue, we're going to average the saturation, and we're going to average the brightness of all 3 of those submats. We're then going to just get the hue channel, or the first channel, and we're going to save that to a simple array. And then what we're going to do is we want to check which one is the largest value. Because our team shipping element was a unique color, it allows us, that will not be on the other 2 zones, it'll allow us to check which one is, the one containing our unique color will be the one with the largest amount of value. And then we save that to a simple variable that we can access via a getter.
Okay, now time for autonomous navigation, explaining the different systems for autonomous position tracking. Next slide, please. So what is odometry? Odometry is the use of sensors to determine the robot's position. Normally, odometry is something called dead wheels, which are wheels that are under the robot that don't actually cause the robot to move, but they move along with the drivetrain to track the robot's position using rotary encoders. This allows for localization, which is autonomously tracking the position of the robot. And this is essential for advanced autonomouses. This is an example of a holonomic drivetrain that uses odometry wheels. You can see 3 dead wheels on this drivetrain to create this localization system. So the first type of odometry you could use is just drive wheel odometry. This means your robot drivetrain has no dead wheels, and you're just relying on the encoders of the robot's drive wheels to track its position. So the advantages of this is that no dead wheels are needed, but the disadvantages is that it's the least accurate system to determine robot position, because mecanum wheels experience slip as the robot moves, so it won't be able to determine exactly where the robot is as the movement goes on, as it'll begin to slip. Here shows a drivetrain that uses the motor encoder values for localization. Next is 2 dead wheel odometry. The benefits is you need 2 dead wheels as opposed to 3. The drawbacks is because 1 dead wheel is tracking the y direction motion and 1 is tracking the x direction motion. So you can get an exact coordinate position of where your robot is on the field, but since you don't have a 3rd dead wheel, you can't track the orientation of the robot. That's why you need to rely on the IMU sensor to do this. The big issue of this is that IMU communicates through I2C, making it slower. This means that it'll slow down any position tracking loops you have, which will decrease accuracy over time. And now finally is a 3 dead wheel odometry. The benefits is that it's the most accurate robot localization system, and its negatives is that you need 3 odometry wheels to utilize it. So it could be more expensive and take up more space on your drivetrain. Here's just a drivetrain that uses 3 dead wheels. 2 to determine, they all work together, 3 of them, to determine the robot's coordinate position and orientation on the field. So what types of odometry are there then? So you can see a breakdown of each of the odometry systems, with the least accurate but least parts being the no dead wheel odometry, only motors and coders, and the most accurate but most parts being the 3 dead wheel odometry. But how do you make odometry work in your team's code this season? So there's many different methods for doing this, one of which is pure pursuit. Pure pursuit works by teams defining something called waypoints, which would be these points on this line here, and then it connects them to make a path for the robot to follow. An important thing to note about pure pursuit is the robot only roughly follows this path. How it works is there's this circle around the robot, and the robot will see which point around in this circle connects with this line. And then it'll travel towards that point of connection, and based on how far away it is, that'll control the velocity of the robots. Could you continue? So this is a better diagram of how it works. So you first define waypoints by just having coordinates around the field, like 14, -3, as shown here. And then pure pursuit would connect them with this blue path here, generated with the waypoints. Next, a circle would be around the robot. You can adjust the size of the circle for how closely you want it to follow the path. And finally, it'll determine the point of intersection ahead of the robot, and the robot will travel towards this point. And the distance between the robot and this point will determine the robot's velocity to allow it to roughly follow this path. If you want directions on how to get started with pure pursuit, please go to this link here. Oh, we have a QR code at the end, so you can just scan it and have access to these slides. Roadrunner it also is another system for localization of the robot. So you still plug in coordinates, and you can also plug in an orientation of the robot if you want. So Roadrunner, what it does is it generates the most efficient path for your robot to move to a certain point. So it often has the robot move in splines while spinning in circles to move there. Here you can see one of the paths Roadrunner would generate, and it has this smooth curve that'll retains continuity of the robot's motion, maximizing efficiency. Roadrunner, how it works decoded is you just like, if you wanted to use splines, you'd use spline 2, and then you plug in the coordinate position. You can also give orientation. There's a variety of different methods. And here's some instructions to incorporate Roadrunner. Sean has a lot of experience with Roadrunner as he used it last year, so would you like to talk more about that?
So Roadrunner is a very powerful library. It is split into two sections, a localization library and a pathing library. So they have several pre-built localization methods, like the ones Jensen just discussed. So 3-wheel odometry, 2-wheel odometry, or drive encoder odometry. You can also write your own localizers if you want to write something unique, but generally teams stick to those 3 pre-made ones. It's also a very powerful pathing library. You define points ahead of time in the init method of your team's code, and then you define points, and then at runtime it's going to generate those, and then it's going to follow those paths. Roadrunner can be kind of complicated to set up. It is many hours of tuning, but once you have tuned the robot is accurate, fast, and very reliable.
So Roadrunner, as Sean mentioned, can be very complicated to set up. So for newer teams or teams trying to get into localization, we developed something called Coyote, which is another position tracking system. So how it works is you just have a go-to position method where you'd put the coordinates you want the robot to go to as well as an orientation. What's good about Coyote is Roadrunner, you can't control the robot's speed as it's just determining the most efficient path, but with Coyote you can. So you could have it go slower or faster. It's also much easier to work with as all it is just the go-to position method where you plug this information in. So this would be for teams just getting into it, and it has also the advantage of not generating paths before the start buttons hit. This means that you won't have to wait for the paths to be generated every time you run your auto, but also it can have on-the-fly adjustments. For example, if our robot collided with another team's robot during auto, our robot would actually adjust for that. That happened during a match for the team last year with Working Title, where their robot collided with us, but it was able to go around them, so both our autos continued functioning. If you want to learn more about Coyote, please email us at 10635uk@gmail.com, and we will send you the GitHub link when we get that finished. Would you want to go to the Q&A? So there's also a QR code link, but any questions? Yeah, you can just scan this and have access to our slides.